Hi, I'm James Pond, Principal Product Manager at Ansys Lumerical, and I'm going to tell you about some recent innovations in Ansys Lumerical PDK-driven workflows. For some background, we know that the market in integrated photonics in general, and silicon photonics in particular, has been growing rapidly in recent years and is expected to continue to grow rapidly in the next few years at over 40% per year. This is mainly driven by growth in the transceiver market, but other applications such as LiDAR, biosensing, artificial intelligence, and even quantum computing are also emerging and will play an increasingly important role in the future. At Ansys Lumerical, we offer a comprehensive set of products for integrated photonic design. We have multiphysics physical solvers to design and optimize components, and tools for the simulation of larger scale photonic integrated circuits and systems. In addition, we have a variety of interoperability, cloud, and HPC features. The integrated photonics ecosystem has become increasingly mature over the last decade. There are now a variety of foundries that offer PDKs created from a combination of physical simulation, experimental results, and information about the process and technology. There are also a variety of workflows for schematic capture, circuit and system simulation, layout and mask generation, and verification. This allows a user to design, optimize, and fabricate photonic integrated circuits reliably. At Ansys Lumerical, we focus on the areas of simulation and optimization of components and the generation of photonic compact models for the PDK that can be used to perform the circuit and system level simulation. Our tools make it possible to go all the way from the design and optimization of advanced components such as grating couplers, lasers, modulators, and photodetectors to system simulation where we can perform signal integrity analysis or consider the impact of fabrication errors on yield. We offer a variety of different workflows. For example, we can work in our own schematic environment using interconnect, where we can perform time and frequency domain analysis, corner analysis, and Monte Carlo analysis. In addition, we offer workflows with Cadence and Mentor graphics, which make it possible to design and simulate a full electronic and photonic system. Here in the upper right, we can see an example of a full co-simulation of the electrical driver and the photonic circuit. What we're seeing is the impact of timing errors between the electrical signals on different electro-optical modulators, which must be precisely controlled in order to preserve the signal integrity. We also collaborate actively with a variety of foundries, both in silicon and indium phosphide material systems, to provide advanced PDKs. One area where we've made great progress recently is in custom component design. We find that circuit designers can't just use the off-the-shelf components available in the PDK to make their circuits. Instead, each company has a few components where they have valuable IP. This might be a low-loss grating coupler or a high-speed modulator. Our new flow allows designers to use a foundry process file, which allows them to construct the 3D geometry of a design for one particular process. This means that their designs can be optimized for a particular foundry, and compact models can be generated for these custom components that can be used in combination with the models provided by the foundry. And here at the bottom right, we see an example of a 3D geometry constructed for compound tech. The key way we've enabled all these photonic compact models to work together is with our CML Compiler product. This product takes well-defined data for each component, for example, waveguide properties such as effective index, group index, and so on, or S parameters for different passive components, and compiles that data into models for different simulators. CML Compiler can generate models for both interconnect and Verilog A from the same data source, and this enables designers to use their simulator of choice. It will also generate virtuoso symbols for these models, which is really convenient. Another area where we've made great progress is manufacturing variability and simulation. This is important because the more circuit designers can anticipate issues around process variability, the more they can reduce project risk. Our CML compiler now takes statistical information such as process corners, statistical distributions, and sensitivity data to create compact models that are statistically enabled. In photonics, spatial correlations are critical to statistical simulation. Indeed, we know that there are spatial correlations between the process variations that lead to correlations of the component behaviors. This means that the choice of layout will impact the final yield of a circuit. Now you can take a given layout and extract the component positions back into interconnect. This allows you to enable spatial correlations and see their impact on the final results. And we can see that it can have a very significant impact on the final distributions. Finally, we can visualize correlation coefficients, which helps us to go back to the layout and fix problems before we go to fabrication. Finally, I want to mention a lot of work we've done recently on laser and gain simulation. When designing integrated lasers, our tools are used for a variety of individual components. But here I want to focus on tools which have undergone significant development recently. Our multi-quantum well, or MQW solver, can calculate band diagrams and wave functions, as well as stimulate and spontaneous gain curves at different temperatures. The laser itself, including external cavity or circuit, can be simulated in interconnect using our TWLM, which takes input data from our physical solver, such as MQW. Recently, we've enabled self-heating effects in the TWM model so you can see the power roll-off at higher currents, and we get nice agreement with experimental results. In addition, we've recently worked with Fraunhofer HHI to develop a calibrated SOA compact model using the TWLM, which gives excellent agreement with experimental results across a range of input powers and wavelengths. I hope this has given you an overview of what Ansys Lumerical can do for you in integrated photonic design. Please visit us at our booth or find us on social media.